Hello, my name is Asmarat Adil and I am a student at UCL, and today we wanted to present me and my group a presentation about a recent experiment we have done in the lab and its importance to our everyday life. Before discussing the results of the experiment and the experimental procedure, first let's briefly talk about what is diffusion. Diffusion is the transfer of particles from a high concentration to a low concentration, and diffusion occurs in all states of matter, for example, liquids, gases, and even solids, and it is one of the main ways that mass is transferred in nature and in the industry. To measure the diffusion in solution, we set up a diffusion cell and we added sodium chloride solution to that diffusion cell, about 30 milliliter of 1 mole per liter sodium chloride, and then we placed the diffusion cell inside of a pure water solution, distilled water, and turn on the magnetic agitator, and then we measured the conductivity over time. So on this slide we have the raw experimental data from our experiment, and as you can see, as time goes on, the conductivity steadily increases, and we can represent this data on a graph to see how the conductivity has changed over time. As you can see from the graph, the gradient seems to be fairly stable, and that shows that the conductivity increases as the salt diffuses into the water. So here are the calculations that we did for the first experiment, and we have a difference quotient of 6.568 per minute and a concentration coefficient of 2.53 times 10 to the minus 8 meters squared per second. So the sources of errors for the first experiment are the likely convection from filling and stirring treated as diffusion, which overestimates the diffusion coefficient. Assuming constant driving force when it decreases also overestimates the diffusion coefficient. Uncertainties in capillary geometry and water volume cause a bias flux and diffusion coefficient. For the second experiment, we measured the diffusion of gases, and we did this by setting up acetone in a capillary, and we heated the setup using a water bath so the temperature remains relatively constant, and then we observed the evaporation rate over time. So here is the raw experimental data for the second experiment, and as you can see clearly, the acetone level of the liquid decreased pretty steadily over time, which of course the acetone vapor is vaporizing into the system. As you can see here, we have calculated the difference quotient, which is the time over the change in length, so we can plot it on a graph. So here are the results of the graph, which plots the change in level of the acetone versus the difference quotient, and as you can see, there's a linear relationship which shows that the difference quotient is proportional to the difference in height. So for experiment number 2, these are the calculations, and we have got a diffusion coefficient of 5.2 times 10 to the minus 7 meters squared per second. Some sources of error that you can expect for this experiment are in the microscope reading. For example, when you go on to look at it, you might incorrectly measure the small changes, which might contribute to false data. Evaporation is not purely diffusion controlled. Natural convection and external drafts in the gas column add convective transport on top of diffusion, giving an apparent D larger. A thick stagnant air layer on top of the tube and around the apparatus can add extra resistance to diffusion. The geometry of the apparatus can be not perfectly cylindrical, therefore there might be some slight error. So the key takeaways are that we demonstrated that diffusion is the movement of particles from a high concentration to a low concentration, and the rate of diffusion depends on the concentration gradient and diffusion coefficient.
Some of the real-life applications of diffusion is that diffusion helps in the breathing process. It is also the reason why perfume smell spread among the room, and it is the reason why salt dissolve and spread in water. And in industrial processes, it helps in gas separation and drug delivery.
So, in conclusion, diffusion is a natural mass transfer mechanism, and it plays a major role in industry and our life. Our experiments demonstrate how to measure this diffusion, and understanding diffusion can help engineers in the future.